Okay, in this video I want to talk about uniform circular motion. There are two main assumptions with uniform circular motion, or two main characteristics I should say. And the first one is very obvious, and it's that we're moving in a circle. So uniform circular motion implies that we're moving in a circle, to no one's surprise. The second thing is kind of this word uniform has its own meaning. And in this case, in this physical sense, it means that our speed around our circle is constant. Notice it is not the velocity that is constant. If we're moving around a circle, our direction of motion is changing, and the direction is one of the two parts of the velocity vector. And so the velocity vector is changing, but the speed or the magnitude of the velocity vector is not changing. So let's take a look at this. So first we'll need a circle. So we have a circle here, and let's say that our circle is centered at the origin. I'm not going to put an axis on this to avoid it looking too busy, but somewhere in the center of our circle is our origin, and at some point in our motion, let's say we're just at some point out here on the circle. So I'm going to draw a position vector from the origin to our location on the circle at some given time 1. So there's our position vector. Now, we can also draw a velocity vector at this time t. So we're right here on the circle, but we have some velocity vector. When we're moving in a circle with constant speed, the velocity vector is going to be tangent to our position vector. It's going to be not tangent to the position vector, tangent to the circle. So this is what our velocity vector is going to look like. It's going to be right there. It's going to be tangent to the circle, which is going to make it perpendicular to this position vector, which is in the place of a radius of this circle. And then, so we start here, and our velocity is in this direction around the circle, and our position vector's here. And then as time goes on, we move around the circle. And let's say we stop at some other time right here. Well, then we have a second position vector, and we have a second velocity vector that is also tangent to the circle. Now, this velocity vector is also going to be perpendicular to the second position vector, but since our speed was constant, it's going to be pointing in a different direction, but since the speed was constant, it needs to be the same length as our first velocity vector. So we need another vector that is the exact same length as the first velocity vector. Now, we can get a little more general. We have this idea of a tangent velocity vector that happens to be perpendicular to our position vector, and we can talk about the acceleration vectors in another video as well. But we're just going to stick with these for now. So in order to get some more information about this uniform circular motion, we need to ask some questions about the angles between these vectors. So I have an angle right here between my position vectors. And in fact, we can take our velocity vectors. Remember, we can move vectors around without changing their meaning. So this is my velocity vector, my second velocity vector. And here's my first velocity vector. We have some angle. I lost my arrows there. Let's try that again. We have some angle here between our velocity vectors. So we want to know more about these angles, the angle between our velocity vector and the angle between our position vectors. And in order to get some more information about that, we're going to make a copy of this entire picture here and move down to a new page. So here's that exact same picture, and I am just going to focus on the vectors. We know that they are the vectors representing uniform circular motion, but I just want to pay attention to the vectors. So if we're just paying attention to the vectors, we can go ahead and get rid of this circle. Now, again, we can pick up and move vectors without changing the idea of them or the information they carry. And so since we're interested in the angles between two vectors, I'm going to put vector 2 right here together with our velocity vector 1. And I'm going to change the length of these vectors. Now, I am going to change the length of these vectors, but what I'm not going to do, I'm not going to change their direction. Since we're currently interested in the angle between the vectors, I'm just going to make them a little bit bigger so they're easier to work with. But I'm not going to change their direction, and so their angles are going to stay the same. So here's what I'm going to do. Let's get rid of these arrows here just to clean it up a bit. I'm going to extend this vector down here, making careful not to change the direction at all. And I'm going to extend, make sure it locks back into place where it was, this vector down there. Then I'm going to extend this vector, making sure its position or its direction does not change, right here. And so this will be a little bit easier to work with. And the second thing I'm going to do to make this a little bit easier to deal with is I'm going to make a copy of our first and second velocity vectors, and I'm going to slide them over here. I'm going to slide them over here. Now, this is still pointing in the direction of my second velocity vector, and this is still pointing in the direction of my first velocity vector. But let's see what we can do here. Remember, what we're interested in is the angle between our velocity vectors and the angle between our position vectors. So let's take a look. We said up here that the velocity vectors were tangent to the circle. And since the position vectors are starting from the center and they're basically 2 radii of the circle, any line tangent is going to be perpendicular to a radius at the same point. So our velocity vector 1 is perpendicular to our position vector 1. So we go back down here, and remembering we did not change the direction of these vectors, we have that our velocity vector 1 is going to be perpendicular to our position vector 1. So we can mark this as a right angle. So this angle here is a right angle. Now, similarly, the same thing is going to be true for velocity vector 2 and position vector 2. They're at the same point on the circle. The velocity vector is tangent, the position vector is a radius, so they're going to be perpendicular. And coming back down here, here's the direction of our position vector 2, and here's our velocity vector 2, and so the angle between these two is going to be a right angle. Okay, so we have one more angle to consider before we can make our conclusion. So now let's look here. We have this velocity direction here, velocity 1, which is the exact same as this velocity here, this velocity 1. We just made a copy of it. Now, both of these copies of our velocity 1 intersect this second position vector. So the velocity, the one on the left, intersects right here, and this velocity line, pointing in the exact same direction, intersects right here. Since they're copies of the same exact line, and they're intersecting one line, we also know that this angle here must be equivalent to this angle here. It's the exact same idea. If we want to kind of throw it back to geometry, what we have are 2 parallel lines, this velocity 1 vector and this velocity 1 vector, and they're being intersected by a transversal. So you could throw that back to geometry, but now we know that this angle is identical in measure to this angle here. But now we have something happening that we can make use of. Let's take a look at this triangle right here. So this triangle, well, can't get my laser, right here. Let's try that one more time. Okay, this triangle right here was giving me troubles. So right here, we have a triangle where one of the angles is the angle between our position vectors, one of the angles is a right angle, and one of the angles is the angle between velocity 1 and position 2. But now let's look at this triangle right here. In this triangle, we also have a right angle, and we also have an angle that's defined by velocity 1 and position 2. So this angle is identical to this angle, and this angle is identical to this angle. But we know that triangles' angles have to add up to 180 degrees, and since this is the only angle left in this triangle, and this is the only angle left in this triangle, we know that the two angles in red must be identical, and that's an extremely important piece of information. We know that the angle between our velocity vectors and our position vectors for any 2 points along our circular motion, they have to be identical, and that's an important fact that we can make some use out of. Now, we showed that these two angles are equivalent mathematically because I think it's better to get a mathematical sense of why this is true. We used the fact that triangle angle measures have to add up to 180. And just to show that this is in fact correct, this is not a very mathematical way of doing it, but it still helps to get a visual. If we erase the circle here, and we took vector 2 and placed it on the tail end, or the start of vector 1 right there, then we can take this here and rotate it, and get rid of our sideways letterings here. And if we put this and line it up with our position vectors, we see that the angles are in fact identical. And that's not just going to be because I chose special points on our circle or anything. We could have chosen any 2 points on the circle, drawn the position vectors, drawn the velocity vectors, and the same would have been true. Now, the fact that we have this means we can do some pretty interesting stuff. So again, I want to go down here, and I just want to take a look at our vectors. So what I'm going to do is do the same thing we did earlier, but now what do I have? I have some position vectors and some velocity vectors. Now, I could get my change in position vector out of these. We talked about the displacement vector. If this is where I was initially and I moved to here, my displacement vector is going to be the vector from one point to the other. So this vector here is going to be my displacement vector, delta r. And I can do the same thing with my velocity vectors. If my initial velocity was here and my second velocity was here, I can get a change in velocity vector by going from the tip of 1 to the tip of 2. And this is my change in velocity vector. And we're running out of time here, but I want to pick this up in the next video and continue to get an important result about uniform circular motion.